Section 3.7 on page 147 talks about mechanics and electrical vibrations. Consider a vector with components AI plus BJ. Assume that this happened to be AB. So, in short, this is A, this is B, this is theta. This is the magnitude of that vector V. If you recall how this works, well, cosine of theta is the adjacent over the hypotenuse. And I could say here that A is magnitude of V cosine of theta, right? And I could say here is that sine of theta is B over the magnitude of V, and similarly, B would be magnitude of V, the sine of theta. So, I'm going to call this magnitude capital A, just because I don't want to keep on dragging the magnitude of V in my derivation. If I continue on the side, given A and B, if I call this A, which is what the book refers to it, that's the magnitude of V, that would be the square root of A squared plus B squared, Pythagorean. And tan of theta is B over A. Here they limit theta to be between negative pi and pi. Repetition is not allowed. So they limit theta to be between pi and negative pi, including pi excluding negative pi. And we all know that theta depends on depends on the quadrant. Depends on which quadrant you're in. So keep that in mind and it should be fine. If I claim that y equals A the cosine of omega naught t plus B the sine of omega naught t, y would equal, well, this A right here is really A the cosine of theta, cosine of omega naught t, plus, and this B right here, that would be A, remember we called A for magnitude of V, sine of theta, the sine of omega naught t, and we do know that if you happen to have cosine, cosine, sine, sine, that would be A times cosine of theta, cosine of omega naught t, plus sine of theta, sine of omega naught t, and we do know that would be A times the cosine of omega naught t minus theta. I could put those in any order. And that's pretty much what it is. So, in this book, this author specifically they specify u of t to equal a, the cosine of omega naught, plus b, the sine of omega naught t. They say this is r, the cosine of omega naught t minus delta. This is provided in the book, and on your exams, you don't have to memorize that. You need to know what each of those is. So, we should know that r is actually the square root of a squared plus b squared. I just derived that for you up there. This is the amplitude. T, they call, not P, T is, they call it the period. And they call delta the phase shift. And you get that simply by using tan of theta equals tan of delta, so they like delta, equals b over a, the traditional. And omega naught, unlike trigonometry, is called the natural frequency. Now, in trig, frequency is 1 over the period. Natural frequency. In trig, frequency is 1 over the period, but this is slightly different. Alright, and that's pretty much what you need to know on this first batch of problems, but this does come back. Let me do a problem. On page 157 in the book, 2 problems on those, and again, this is provided. Determine omega, r, and delta. So, to write this expression, and here it is. U equal negative twice the cosine of pi, the sine plus sine. The sine, well, if I look for r, I know that is the square root of negative 2 squared plus a negative 3 squared. And that turns out to be radical 13. If I look at omega naught, well, omega naught is simply right there. That would be pi in this case. Again, really simple. And if I look for tan of delta, well, it's crucial that you plot the point, just like you did back in the days in trigonometry. It's crucial that you graph where do you think this is. Well, that looks like you're going to move a negative 2 back and a negative 3 down, which indicates that r is right there. That's very easy to read, right? That's radical 13. And if you say tan of delta is the opposite over the adjacent, right? Delta would be, well, this is a reference angle. Really, it's not delta. You would say, if you plug that in a calculator, the inverse tangent of 3/2, and that, let me see, actually, I could show you. Right, we have this magic tool now. I am in radians, very good. If I take the inverse tangent of 3/2, I'll get 0.9828. 0.9828. And if I really define what theta is, that would be what? We agreed you must approach the angle either from positive or negative left to exceed pi, that would be 0.9828 minus pi, which is negative 2.16. And that's how you find theta. And then you would say, well, u of t is actually radical 13, the cosine of pi t plus minus, because it's always a minus, plus 2.16. And that would be the answer for this problem. Alright, now we're going to move to something a bit. It does use that previous result. Spring mass system. Well, if we talk about a spring mass system, we are looking at a spring. If I attach to the spring a weight, and do you see right there in the center of that weight, I'll call that right there u sub 0. In this book, they're going to assume if you pull it down, that's positive, and if you push it up, it's negative. So with gravity, it's positive. Against gravity, it's negative. Against gravity, it's negative. Correct. Alright? And we're going to have a mass spring, so there's always a mass. So you attach a mass to a spring and you let it rest. Wherever that rests, we call that 0. Initially, that's where you are. Few things to determine. L they're going to use. This is the stretch of the spring beyond its natural length. We did this already. Right? We worked on this already. If I look at the motion of this spring is given by, and m u double prime, remember u is describing the motion, plus gamma u prime plus ku equal f of t, and we know what all of these are. This is provided, of course. You really don't have to memorize that. Well, guess what? We know out of those that m is the mass, gamma is really the damping force, right? This is given a constant. K is the spring resistance. We call it spring constant. And F of t is the external force. And that pretty much describes what you need. Find M, plug it in. Find gamma, plug it in. Find K, plug it in. And that's pretty much it. Keep in mind how this works. Weight is mg. And g happened to be one of two values. It's either 9.8 meters per second squared if you're given the problem in meters or centimeters, or it is 32 feet per second squared if the problem talks about stretching in inches or feet. We do have a special case. When there is no damping. When there is no damping. Gamma equals 0. The motion is called simple harmonic motion. And that turns out to be a big deal. Alright.